Welcome to the lecture series on automated machine learning. First of all, we'd like to talk about the motivation. Why do we need automated machine learning? In short, AutoML. And here we see that from a perspective of machine learning, why it's maybe not easy to use machine learning in the first place. To that end, I would like to start with a quote by Andrew Ng, and he said, most likely inspired by Arthur Samuel, "Machine learning is the science of getting computers to act without being explicitly programmed." I would really like to highlight the later part where we say, okay, we would like to do it without explicitly programming so that we don't have to sit down over and over again for new tasks and start to program something, but more or less the machine is now able to learn from, let's say, data, how to act, how to make predictions, and all of that. If we think about that a bit more deeply, is it really without being explicitly programmed these days? We could say yes, because machine learning models can be trained for different data sets and tasks using the same code base actually, right? You don't have to write different kind of code lines again and again, but you're using more the same kind of model, let's say a transformer model, for different kind of tasks given new data sets. But you could also say no to that, because for different given data sets and tasks, we achieve the best performance by adapting actually a lot of things. For example, the hyperparameters for training. If you think about pre-training and fine-tuning, you often have things like learning rate, batch sizes, maybe even regularization, and many, many more things. And all of these have these little small magic numbers being involved. And depending on how you're setting these magic numbers, maybe your algorithm performs very, very well, or maybe it will fail, or in the best case, of course, achieve state-of-the-art performance. And of course, there's more to it. For example, you can also adapt the model itself, right? Why do you have always to go with a transformer? You could use also different kind of deep neural network architectures, or you go more for classical machine learning algorithms like XGBoost. And even if you say you're going for deep neural networks, there are different kind of architectures, different kind of sizes, operators, connections being involved. So there's a lot of things you could consider and change actually to achieve best possible performance. And of course, depending on very concrete tasks, maybe there are more things to it. Tokenization, prompt engineering, temperature, if you would like to sample from a transformer or large language model. All of these you can change, and depending on how you're doing it, maybe your performance will change drastically. And don't forget to talk about your data, right? So data in real life is not perfect. We often first need to pre-process that, to do some kind of data filtering, normalization, data augmentation, whatsoever. And all of that helps to overall improve the quality of your data, such that your model can learn better from it. Let's give you some examples. Let's talk about SGD as maybe the most trivial thing you're always using the moment you're training a deep neural network, because that's what's responsible for doing the updates of the parameters and weights of a deep neural network. And if you're going to PyTorch in the documentation, you can already see that that has 5 different hyperparameters which you can choose. So it involves something like learning rate, momentum, dampening, weight decay, Nesterov. And all of that even depends on what kind of SGD implementation you're actually using. And if you consider all these kind of magic numbers in your code and packages, you can easily go up to 30 and more hyperparameters. So there are always these kind of very hidden things. Sometimes it's fine to choose defaults or very established hyperparameter settings, and sometimes you have to adapt it to your dataset at hand to really achieve state-of-the-art performance. From a different perspective, if you're thinking more about the architecture, so if you're thinking about the ResNet, very common thing, you have residual connections, also used in transformer networks. You have different kind of decisions you make. For example, if you're doing that for computer vision, number of channels, kernel sizes, padding, strikes, number of resonance blocks, and so on and so on. You can see it again here in my little code snippet, whereas all these kind of little blue numbers are settings you can play with. And not even that, you can also say actually, you would like to duplicate the number of layers by adding more code lines to it, right? So adding more of these layers. So although the REST architecture is well defined and used for many, many years, for more than a decade, you can still adapt it, and sometimes you actually need to adapt it to really get a good modern architecture. Going a bit more deeper into data augmentation, here we have an example for how to compose actually different kind of data preprocessing steps. So some kind of cropping, horizontal flips, and so on, normalization, all of that being involved. And you have to more think that as a pipeline, you're doing several steps, but depending on your data, depending on the initial data quality and all of that, maybe you have to do different kind of things to really achieve state-of-the-art performance also from the data perspective. And of course, that doesn't only apply to training a single network. If you're thinking more on the mindset these days of foundation models where you have pre-training, and more or everything I told you already before is applying to pre-training, but it's also applying if you're doing, for example, fine-tuning, for example, with LoRa. You have different kind of version of LoRa, you have different kind of hypernodes being involved, and also these needs to be tuned if you'd like to achieve best results. And let's talk about the Holy Grail more or less, because that's what many people trying to do these days, saying, okay, let's say we have a data set, and here I have an example from OpenML. Actually, one data set that has a description, so you know something actually about your task. Why not getting or leveraging that kind of information from that kind of task description and simply querying more as large language model, agentic system, whatsoever, and saying, please generate me the code. Right? We don't say we start from a code base and like to make more minor adjustments like hypernode settings or adding more layers or whatsoever. But here it's really about that an AI system, a Gen AI system, should generate the entire code base, and that should then work out of the box very well. I think we are in a state where that gets more and more feasible, although it's not perfect yet, but we will see later on actually how one can do that. With that, let me summarize all of that. So we have seen now we can strive for machine learning approaches that can learn on their own given data. And that's what we then more is called without being explicitly programmed. In practice, however, we often adapt these kind of machine learning workflows to different kind of tasks or downstream tasks even, while changing hypernodes, architectures, data preprocessing, and many, many more things. We will see over and over again in the upcoming videos what that could mean. And depending on how you set these, your machine learning project can be a great success, or in the worst case can complete fail because maybe your model fails to learn actually from your data. It really depends. The nice thing about automated machine learning, as we'll see in the upcoming videos, is that it can support you in how to make these decisions that you can really get to a very well performing machine learning system without a lot of effort. With that, see you in the next videos.